Chapter 13:1 Fundamental Particles and Forces. Scientists once believed atoms were the smallest particles of matter. With the advancement of technology, it became clear that atoms themselves are made up of simpler particles. Today, we believe atoms are made of three basic particles: the proton, electron, and neutron. It's amazing that the incredible variety of matter around us can be built just from three subatomic particles. In Chapter 8, you were introduced to electric charge. In that chapter, we were interested mostly in electric current, which is moving charge. In order to understand atoms, we need to understand just where electric charge comes from. One of the two forces that hold atoms together comes from the attraction between the positive and negative charge. There are two different kinds of electric charge, positive and negative. Because there are two kinds of charge, the force between electric charges can be either attractive or repulsive. A positive and a negative charge will attract each other. Two positive charges will repel each other. Two negative charges will also repel each other. We use the letter E to represent the elementary charge. At the size of the atom, electric charge always comes in units of plus E or minus E. It is only possible to have charges that are multiples of E, such as plus E, plus 2E, minus 2E, minus 3E, and so on. Scientists believe it is impossible for ordinary matter to have charges that are fractions of E. For example, a charge of plus 0.5 E is impossible in ordinary matter. Electric charge only appears in whole units of the elementary charge, figure 13.1. Inside an atom. The first strong evidence that something smaller than an atom existed came in 1897. English physicist J.J. Thomson discovered that electricity passing through a gas caused the gas to give off particles that were too small to be atoms. The new particles had negative electric charge. Atoms have zero charge. Thomson's particles are now known as electrons. Electrons were the first particles discovered that are smaller than atoms. Thomson proposed the negative electrons were sprinkled around inside the atom like raisins in a loaf of raisin pudding. The bread was positively charged and the electrons were negatively charged. This was the first real model of inside of an atom. As it turned out, it was not the right model, but it was a good place to start. In 1911, Ernest Rutherford, Hans Geiger, and Ernst Marsden did an experiment to test Thomson's model of an atom. They launched positively charged helium atoms. A charged atom is an ion, at a very thin gold foil, figure 12.2. They expected most of the helium ions to be deflected a little as they plowed through the gold atoms. They found something quite unexpected. Most of the helium ions passed right through with no deflection at all. Even more surprising, a few bounced back in the direction they came. This unexpected result prompted Rutherford to remark, "It was as if you fired a 5-inch artillery shell at a piece of tissue paper and it came back and hit you." The best way to explain the pass-through result was if a gold atom was mostly empty space. If most of the helium atom hits nothing, they wouldn't be deflected. The best way to explain the bounce-back result was if nearly all the mass of a gold atom were concentrated in a tiny hard core at the center. Further experiments confirmed Rutherford's idea about this hard core. We now know that every atom has a tiny nucleus which contains more than 99% of the atom's mass. Today, we know that the nucleus contains protons and neutrons. Protons have positive charge, opposite of electrons. The charge on a proton plus E and an electron minus E are exactly equal and opposite. Neutrons have zero electric charge. Protons and neutrons are much more massive than electrons. A proton has 1,836 times as much mass as an electron. A neutron has about the same mass as a proton. The chart below compares electrons, protons, and neutrons in terms of charge and mass. Because protons and neutrons have so much more mass, more than 99% of the atom's mass is in the nucleus. Electrons take up the region outside of the nucleus in a region called the electron cloud. The diameter of an atom is really the diameter of the electron cloud, figure 13.3. Compared to the tiny nucleus, the electron cloud is enormous, more than 10,000 times larger than the nucleus. As a comparison, if an atom were the size of a football stadium, the nucleus would be the size of a pea, and the electrons would be equivalent to a small swarm of gnats buzzing around the stadium at extremely high speed. Can you imagine how much empty space there would be in a stadium? An atom is almost empty space. Electrons are bound to the nucleus by the attractive force between electrons and protons. The electrons don't fall into the nucleus because they have kinetic energy or momentum. The energy of an electron causes it to move around the nucleus instead of falling in. Figure 13.4. A good analogy is Earth orbiting the Sun. Gravity creates a force that pulls the Earth towards the Sun. Earth's kinetic energy causes it to orbit the Sun rather than fall straight in. While electrons don't really move in orbits, the energy analogy is approximately right. Because of electric force, all the positively charged protons in the nucleus repel each other. So what holds the nucleus together? There's another force that is even stronger than the electric force. We call it the strong nuclear force. The strong nuclear force is the strongest force known to science, figure 13.5. This force attracts neutrons and protons to each other and works only at extremely small distances inside the nucleus. If there are enough neutrons, the attraction from the strong nuclear force wins out over the repulsion from the electromagnetic force, and the nucleus stays together. In every atom heavier than helium, there is at least one neutron for every proton in the nucleus. There is another nuclear force called the weak force. The weak force is weaker than both the electric and the strong force. If you leave a single neutron outside the nucleus, the weak force eventually causes it to break down into a proton and an electron. The weak force does not play an important role in the stable atom, but comes into action in certain special cases when atoms break apart. The force of gravity inside the atom is much weaker than even the weak force. It takes a relatively large mass to create enough gravity to make a significant force. We know that particles inside an atom do not have enough mass for gravity to be an important force on the scale of atoms, but there are many unanswered questions. Understanding how gravity works inside atoms is an unsolved mystery in science. How is an atom of one element different from an atom of another element? The atoms of different elements contain varying numbers of protons in the nucleus. For example, all atoms of carbon have 6 protons in the nucleus, and all atoms of hydrogen have 1 proton in the nucleus, figure 13.6. Because the number of protons is so important, it is called the atomic number. The atomic number of an element is the number of protons in the nucleus of every atom of the element. Each element has a unique atomic number. On a periodic table of elements, the atomic number is usually written above or below the atomic symbol. An atom with only 1 proton in its nucleus is the element hydrogen, atomic number 1. An atom with 6 protons is the element carbon, atomic number 6. Atoms with 7 protons are nitrogen. Atoms with 8 protons are oxygen. And so on. Because protons and electrons attract each other with very large forces, the number of protons and electrons in a complete atom is always equal. For example, hydrogen has 1 proton in its nucleus and 1 electron outside the nucleus. The total electric charge for a hydrogen atom is 0 because the negative charge of the electron cancels the positive charge of the proton. Each carbon atom has 6 electrons, 1 for each carbon's 6 protons. Like hydrogen, a complete carbon atom is electrically neutral. Isotopes. All atoms of the same element have the same number of protons in the nucleus. However, atoms of the same element may have different numbers of neutrons in the nucleus. Isotopes are atoms of the same element that have different numbers of neutrons. Figure 13.7 shows 3 isotopes of carbon that exist in nature. Most carbon atoms have 6 protons and 6 neutrons in the nucleus. However, some carbon atoms have 7 or 8 neutrons. They are all carbon atoms because they all contain 6 protons, but they are different isotopes of carbon. The isotopes of carbon are called carbon-12, carbon-13, and carbon-14. The number after the name is called the mass number. The mass number of an isotope tells you the number of protons plus the number of neutrons. Radioactivity. Almost all atoms have 1 or more isotopes that are stable. Stable means the nucleus stays together. For some complex reason, the nucleus of an atom becomes unstable if it contains too many or too few neutrons relative to the number of protons. If the nucleus is unstable, it breaks apart. Carbon has 2 stable isotopes, carbon-12 and carbon-13. Carbon-14 is radioactive because it has an unstable nucleus. An atom of carbon-14 eventually changes into an atom of nitrogen-14. If an atomic nucleus is unstable for any reason, the atom eventually changes into a more stable form. Radioactivity is a process in which the nucleus spontaneously emits particles or energy as it changes into a more stable isotope. Radioactivity can change one element into a completely different element. For example, carbon-14 is radioactive and eventually becomes nitrogen-14. In alpha decay, the nucleus ejects 2 protons and 2 neutrons, figure 13.8. Check the periodic table and you can quickly find that 2 protons and 2 neutrons are the nucleus of helium-4. Atom. Alpha radiation is actually fast-moving helium-4 nuclei. When alpha decay occurs, the atomic number is reduced by 2 because 2 protons are removed. The atomic mass is reduced by 4 because 2 neutrons go along with the 2 protons. For example, uranium-238 undergoes alpha decay to become thorium-234. Beta decay occurs when a neuron in the nucleus splits into a proton and an electron. The proton stays in the nucleus, but the high-energy electron is ejected and is called beta radiation. During beta decay, the atomic number increases by 1 because 1 new proton is created. The mass number stays the same, but the atom lost a neutron but gained a proton. Gamma decay is how the nucleus gets rid of excess energy. In gamma decay, the particle emits pure energy in the form of gamma rays. The number of protons and neutrons stay the same. Take a moment to answer these questions.